In this video, we'll show the collision between two objects when they collide elastically. So what we've done is replaced the needle and clay apparatus that can go on the carts that would have otherwise made for a perfectly inelastic collision. And we've replaced them with a blade, not a sharp blade, a dull blade, but I call it a blade and rubber band attachment. So the gliders come together, and then momentarily some of the kinetic energy of a glider is converted into elastic potential energy, and if the rubber band is ideal, then when they rebound back off each other and the collision's finally over with, all of that stored elastic potential energy comes back into kinetic. So not only is momentum conserved in collisions like this, but mechanical energy, specifically in the form of kinetic energy, is conserved. Momentum before the collision equals momentum after the collision. That's nothing new. But if the collision's elastic in this way, the total kinetic energy of the two carts before the collision equals the total kinetic energy after. So let's see one special case of this one. Here we once again have the 1-to-1 mass ratio, and I'm going to leave this one at rest. Turn on the air, make our system isolated. Oh, and one more thing. Often when I try to send one in motion, instead of pushing it this way, I like to push it in that direction, and then it bounces off the end of the track, and then levels it out when it comes back this way. So it might look silly that I push it this way to make it collide with this glider, but that's exactly what I'm going to do. Ah, there, did you see it? This one stops nearly dead in its tracks and gives all of its momentum to this one. And you can see that would satisfy the condition that not only conserves momentum, but also conserves kinetic energy. One more time. Perfect. Well, you've seen collisions like this before. If you've played billiards, right? Sometimes the cue ball and the 8-ball line up perfectly, and it's a straight shot, and the cue ball stops dead in its tracks and gives all its momentum to the 8-ball, and you win the game. Hey, here's another special case. If I have a very heavy glider with the extra masses on it, such that its mass is exactly 3 times the mass of this glider, and that's the way we've worked it out, then you get a really curious result. There's another video I'd like you to watch where I've worked this out mathematically. And it turns out that if I'm allowed to make up some numbers, if I can push this glider at 10 meters per second, so we've got a glider that's 3 times as massive at rest, and the glider of mass m that's going with a speed of 10. When they hit, they bounce apart in opposite directions. This one will go half its initial speed in that direction, so a speed of, or a velocity of negative 5 meters per second, right? It was coming in at positive 10, bounces back at negative 5, half of its initial speed in the other direction. This one will go forward at positive 5. So notice the relative velocity of the gliders. This one's at rest, and glider number 1 is moving at 10 meters per second, so relative to one another, they're coming together at 10 meters per second. After the collision, if this one goes negative 5 meters per second and this one goes positive 5, now they'd be moving apart relatively at 10 meters per second relative to one another, right? To have something go 5 that way and this one go 5 this way, relatively speaking, compared to one another, they're moving apart at 10 meters per second. This is always the result of an elastic collision. Not just if the mass ratio is 1-to-3, in any elastic collision, the relative velocity before the collision is equal in magnitude to the relative velocity after the collision. But it's only in the 3-to-1 ratio that the velocities are equal and in opposite directions. So I made up the numbers of 10 and it goes 5, 5. But if this one just had a velocity, we'll just call it v, then this one's going to go negative v over 2, and this one will go positive v over 2. That's for the 3-to-1 ratio. Let's see it. Yeah, it looks about right. It looks about half and half in opposite direction. Now watch this. This is fantastic. Boom. It returns to the original situation. The one at rest, and then they hit, and now negative 5 and positive 5. They go to the end of the track, and then it's back to 0 and 10. Now we got it coming in at 10 meters per second, and they go apart negative, and it will just continue repeating this process. So that's an interesting collision I thought you might appreciate.